Chapter 7, sections 1, 2, and 3. What questions do you have for me about any of these problems? Yes?
Section 7,
26. 7.1.26 says, W squared log W, right? W squared ln of W?
Yeah, sorry.
Okay. Okay, doesn't matter. You can use X. I don't care. One to two? Great. So, two ways to attack this. We can do the indefinite part and then worry about the numbers, or we can deal with the numbers as we go along. Either way. I'm going to leave it in this definite integral notation and deal with the numbers as we go along. So, integration by parts, yes? What's U, what's dV? Great. So now I need to fill in the other parts. Du, V. Great. UV evaluated, because this is a definite integral, minus definite integral, V du. You good from here? Or do you want me more?
Can you, so when I'm doing that, I went through and plugged in for the first part. How do I have to alter it on the two? Because I just did the.
Oh, you don't have to do any alteration here. I just have to do this integral.
So you just have to plug them directly into both of them and you don't have to change
What you're thinking of is when I do a U substitution, I have to change to be U, right? But these are all still X's.
So it's still have to be minus FA.
Yeah, but I still have to do the integral here, don't I?
Yeah.
Right, but once you do the integral here, then it's f of b minus fa. You're still doing, it's all in X, so there's no changeover to have happen.
And it's be, it would be 112 x to the fourth ln of 4. I try to do it, like I already plug the numbers in. I guess.
So let's leave this alone for the moment.
Yeah.
Let's simplify that.
I just did 1/3 and x to the third.
So there's no logarithm in that term anymore. There's no 1 over x at all, which means when I do this antiderivative, because I get another over 3, right? Now I can plug in. I think, I'm not 100% sure, but I think what you did is you tried to integrate this again as well. I don't have that part's already done being integrated, so I don't have to integrate that anymore. So once that part is done as UV, I'm done doing the antiderivatives in that section.
So if you do integration by parts, you never need to mess with the bounds.
As long as you do not change the variable. In a regular substitution, you're switching letters, right? We were still calling these U and V, but down here, all these pieces are still in X. So I don't have to mess with the bounds. I only mess with the bounds when I actually change the letter. So if I'd left it in W, it would still all be in 1 and 2. And I can just leave it like that. We have a collision of ideas here. Not a bad collision, but you are conflating two things that don't need to go together at this point. More questions? Yes, Jim. 7.162. Okay. 62 requires me to go all the way back to chapter 6, section 3, where we did rotations, volumes of rotation. Because it says, that we're going to make a solid of revolution. You remember me with the little paper toy football thing that we solid? Because this one's going around the y-axis, instead of using discs or washers, I'm going to use cylinders. It even says at the top there to use the cylinder notation, right? Yeah. So let's turn back to chapter 6, section 3, and steal the cylinder idea again. This is page 450, and there's a formula on page 451 that says if I'm rotating the region under f of x, then this is my formula for revolution. So I'm gonna bookmark that and I'm gonna use it. Page 451. So with that in mind, I need to draw a picture because I suck at doing this without a picture. So graph for me, graph e to the x, graph e to the minus x, and graph x equals 1. Tell me what that picture looks like. See why we need them? Mode. At the very top, it says normal psi eng. Go down to the fourth line. Fourth line says func par pol sec. Yeah. Make sure FUNC is highlighted. Hit enter. Yeah. Now go back to y equals. I know that mode. I know exactly whose calculator you were using and what they were doing last semester, if that's where they are. Okay, so I have these two equations because I can't graph x equals in my calculator. I'm just going to graph these two. And on my standard window, this is what I see. With me, Jack? Okay, it says x equals 1, right? As the other piece? Yeah. X equals 1 is a vertical line. That means I'm going to draw here, and you see that little wedge next to my finger? That's the piece I'm concerned with, this little piece right in here. So let me make a crappy sketch. I get a picture that looks like this. And this little flag with curved tops and bottoms, that's the region in question. That's the piece I want to spin around the y-axis. Which means I'm going to fold it over. It's going to end up over here on the left. So when I move that from right to left, there's another little piece over on that side. I even turned the R backwards, right? And it spins around, and boy, did I make a crappy picture, around this way. The piece on the right and the piece on the left should be the same shape. As you can tell from my artistic endeavors, I didn't manage that. We good so far? What's the formula for doing a cylinder integral? Integral symbol. Okay, so when I taught this, and I know it's been long enough, or some of you didn't have me for this, I thought of my cylinder as a physical object. So here's my cylinder, right? And I'm adding up a bunch of these shells, which means I need to know how big this shell is. What is the volume of this piece of paper? Not of the thing inside the piece of paper, of the paper itself. Paper's a rectangle. It's got a thickness, a height, and a width, right? If I'm going this way, we can think of it as being stacked like this. I mean, thickness is a little bit of x. A little bit of x. Radius from the middle out to a point x. That means that that distance across the bottom of my cylinder is the circumference of 2 pi radius. And height. Height. What's f of x in this picture? So that's this one? Yeah. But what about this one? I have to go from here to here. It's not one function because e to the x would go all the way to the x-axis, wouldn't it? I want to go all the way to the x-axis. I want to go from the top one to the bottom one. So what this f of x is it's that height. What's the expression to give me that height? That should be a plus x, not minus x. Screwed up. Yes. So that's my height. And then I have x and I have f of x. Now what are a and b? A and b should be the edges of the triangle I called R. Left edge and right edge.
0, 1.
Exactly. Okay, wait a minute.
So which ones will want to use the top function or the bottom function?
Say again.
Which one will want you put in like the top function and the bottom function?
If my picture was turned sideways. But most of the time we put numbers for our limits. I'll do more of doing limits that aren't numbers, but that's Calc 3. That's not this semester. That's integration by parts, isn't it? I have an e to the x thing and I have an x thing. There you go. You're set up to do integration by parts. We can kick butt on this one. What's u, what's dv, and off we go. Now, you could, if you wanted to, break this into 2 separate pieces. Because you could do this integral as a difference of 2 quote-unquote simpler integrals. But again, that's an option. You don't have to do that. But you can do this one and do integration by parts on each one with a different u and a different, with a different u and a different dB. Better? All right. I do remember that in some undergraduate calc classes, particularly the AP classes, they don't do cylindrical shells at all. Which I think is dumb because it works really well in some of these problems. But I didn't write the AP curriculum. Yes? Okay, well, go through the order of our mnemonic. Logarithms, no logarithms. Inverse trigs, no inverse trigs. Polynomial, there's an x. U is x, dB is the e to the x stuff. You're very welcome. E to the x minus e to the minus x. If you're doing it as one integral, or you can do it separately, and then over here dv will be just e to the x, and over here dv will be e to the minus x. So it's up to you whether you do it as one or two. In a very real sense, and I'm going to show my age again. There is a black and white cartoon called Felix the Cat. Felix the Cat has a suitcase, a black suitcase, from which he can pull out anything he needs to make the situation funny. Not fix it, but to make it funny. And so Felix the Cat has his magical bag of tricks. I'm building your magical bag of tricks. They're just integrals instead of funny. So how you choose to use that trick is up to you, but you have all these new tools at your disposal. Integration by parts, I have substitutions, I have these trig substitutions, I have all the trig formulas I need to make those easier, and away we go. Better? More questions?
You do section 7.2, question 2.
7.2, question 2. Sine cubed cosine to the fourth, yes?
The way I attacked it was trying to get sine squared cosine of 1 sine, and I just couldn't get it.
Okay, I like that. So I'm going to do that. So this is 2. So this is the integral sine squared cosine to the fourth, 1 extra sine, and a d theta. Beautiful, wonderful, I like that idea. That's a great place to start. If I do that, then there's a u substitution floating around in here. I think so. Because you already have an extra sine theta out at the end, right? So I'm pretty sure in my head at least, this should be du. Or at least it should be partially related to du. And if the sine is the du, then what should be u? I think I'd be better off with u being cosine. So let's try and set that up. If u is cosine of theta, what's the derivative of cosine? Leo. I got that extra minus. So minus du is sine theta d theta. So really, I'm missing a minus sign. I'll fix that. What that means is that all the rest of this garbage should be cosines. Gesundheit. How do I fix that to get rid of a sine squared and bring in cosines? My favorite Greek geek. So what would you get?
I did it so that I had sine theta cosine theta to the third.
Right, but I think that, let's not do that. Let's try and turn everything to cosines. So how would I turn that into a cosine? Careful. Order matters. Remember, it's sine squared plus cosine squared equals 1. So to get the sine squared alone, it's going to be 1 minus cosine squared. But now everything except that last sign is in cosines, yes? Which means I can do my u substitution. And if you really want to, you can take that minus sign and put it out front. But the best part about this is that's power rule. All I have to do is distribute. It works. So while I could do sine theta, sine cubed, cosine cubed, that trick really only works best when the powers are already equal to begin with. And I didn't have that here, so that was much harder. Better? More questions? Yes. 24. That's the tangent squared tangent to the fourth one, yes? Okay. So what did you try? Secant squared x tangent squared x. How do I get there from here? Okay. That's kind of an issue, Jacob. You got to be able to read your own handwriting. But let's run with that. There's a Pythagorean identity for tangents and secants, right? So if I have sine squared plus cosine squared equals 1, that means that tangent squared plus 1 is secant squared. I divided everything by cosine squared. So if I could get tangent squared plus 1 somewhere in there, I'd be able to get rid of it and put it at secant, right? So if I factor out tangent squared, what's left is 1 plus tangent squared. So I'm absolutely thrilled that you got to see tangent squared, secant squared. Because that's exactly where I want you to end up. What's Drew, tangent? I have a u and a du right here, don't I? Yes. So that's exactly the right place to be. And now I'm 1 u substitution away from being done. Better? Yes, ma'am. Yes, because that tangent squared over there just needs to be tangent, so it's going to be squared to the integral itself. But once I get to power rule is the one I know by heart. I'm really happy to do power rule.
You do 20 is
20. X sine cubed x? That looks scary. I promise it's less scary than you think. Because your first reaction is say there's a sine cubed, I should split one off, right? Do the odd thing. What do I do with that extra x? What this really is as written, this is integration by parts. If I go to set that up, it should be u equals x. Polynomial before trig, right? Logarithm inverse polynomial exponential trig. But that means that dv is sine cubed of x dx. So in order for me to get v, I need to do the integral of this. And that's where I do the split off with the extra trig function. Inside my integration by parts is a trig integral problem. They were hiding it from me, those rat bastages. That's an odd power. I split one off. And now we're back to what we did in the previous version of the problem, right? With the sine cubed and the cosine to the fourth. Only this time there's no cosine to the fourth to worry about. Pythagoras to the rescue again.
That's just the answer for V.
Right, then I have to do uv minus v du, and I'm going to have to do the integral of v du. What's du? I didn't even write that part down. Oh. Which means this thing is going to have powers of cosine in it. That's what I'm going to get from here, right? So there'll be another trig integral for the integral of v du. Stack them on top of each other, one technique inside the other. Your eyes will cry, your sides will shake, your heart will go pitter-pat. Watch and feel, it's the wonderful cat. You can put that on the canvas page at some point. Leo, question?
I was thinking how with my 20 here, thinking how I broke up and made sine cubed, like sine squared is 1 minus cosine squared of x times sine of x.
Yes. And then we do a u substitution here. Absolutely. U is cosine, u is sine. And that'll be 1 minus u squared.
So you have to do a U sub to even get your V to do the integration by parts.
Yep. I'm going to take you back to Chem Lab. You're not allowed to throw anything at me. I need to build this reagent and this compound to then do this reagent to then do this compound. See how it stacks? That's really all I'm doing here is I'm stacking them up on each other. You're exactly right, Leo. That's exactly what we continue with in that problem. Excuse me. And then we have V, then we can do the integration by parts, and then we can look at the remaining integral in that and see how it's done. You're exactly in the right place. More questions. Ask me more. Seven, 2. 36 cotangent cube. Okay. Cotangent cubed. All right. I'm going to think through this the same way I did with the tangent one earlier. It would be nice if I had cotangents and cosecants together. So over here, to set this up, divide everything by sine squared. 1 plus cotangent squared equals cosecant squared, right? So if I pull off one cotangent, I can take the cotangent squared and convert it to be cosecant minus 1. Sorry, cosecant squared. Now, I like thinking of this as two separate integrals. So I'm gonna make this two pieces. I'm gonna do the integral of cotangent of x cosecant squared of x minus the integral of just cotangent x. So I basically multiplied the cotangent and then split it up into two pieces. You with me so far? So in the left, I need to go back to my trig derivatives. What's the derivative of cotangent? This is why we have a formula sheet. Seriously, I don't remember this. I got to go look at it. Almost. Negative cosecant squared, which means this is a u substitution. So I now know how to do that left integral. What do I do on the right integral? I could, but that wouldn't be productive. I could cry a lot. I just don't think it's worthwhile. We did tangent in class last week. So let's change it to cosine over sine. That's actually a different u substitution, isn't it? What's the derivative of sine? So I could write this as 1 over sine x cosine x dx and do a different u substitution for this part. One u substitution over here, a different one over there, but they'll both work. That's why I split them up. So if I'm going to do different substitutions, I should have them in different places so I can keep track of my. So over here, I do u equals sine x and du equals cosine x dx. Maddie, now. I'm going to get an ln because I got a 1 over. But now is where you make the decision. Do I change the numbers or not? Because now I'm going to change letters. If I change this letter to be U, then I can change the numbers. I don't have to, but I could change the numbers. If I do that, I either have to write this, or what's sine of pi over 4? That's why you have a unit circle on the paper in front of you. On the other side. I cheated. I know I gave it to you, Maddie. Okay, sine of pi over 4 is root 2 over 2. Sine of pi over 2 is 1. If you do the left integral, after you do the logarithm and all that, you got to go back to x, and then you plug the numbers in. You do the right integral, you don't have to do that, you can change the numbers. But now over here, I can do the same thing. There's my u substitution. Or I need to know the value of cotangent of pi over 4 and cotangent of pi over 2. Do you know those numbers? Me neither. So let's do it this way. But if you knew the numbers for cotangent, you could use those instead. But I'm just going to subtract the numbers when I'm done because it's all going to be a number in the end, right? If I'm doing a definite integral, my result is a number. I don't care what letters you used in the middle to get the number. It's your choice. You absolutely can. Wait until the end and plug all the same number in every place. I don't have a problem with that. But again, magical bag of tricks. Which way do you want to do it? They're all equally valid as long as you do them correctly. Cotangent is cosine over sine. Cosine of pi over 4 is root 2 over 2. Sine of pi over 4 is root 2 over 2. That makes this a 1. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. That makes this a 0. I don't care whether you do this integral or this integral, you're going to get the same answer. I don't care if you do this integral or this integral, you're going to get the same answer. Whatever number you get over here, subtract whatever number you get over here. Okay, does that make more sense? All right. I promise, Maddie, write it out the way you want to do it, whichever two of those 4 integrals you want to do. Most people do these because they don't like changing limits as much as I do. I adore changing limits, but I'm weird. More questions?
You want to do 7.140?
From 0 to My first question. This is in the chapter on integration by parts. Where's my freaking integration by parts here? Secondly, even if I were just thinking about this as trig functions, I'd be pissed off because I've got cosine of 1t and sine of 2t. And I don't like it when they mix periods like that. That's not nice. So I would rather have this all be in either 2t or all in 1t. Kind of hard to change this one because it's part of the E, so I'm probably better off changing this one. Double angle formula. Sine of 2t equals. Hey, wait a second. Cosine is in this problem twice. Sine's only in this problem once. I see a U substitution staring at me. What U substitution? Since my eventual goal is probably integration by parts, I'm going to use a different letter. Instead of U, I'm going to use X. If I'm looking at more cosines than sines, I probably want to use that one sine for the du part. So let's make X be cosine of t. What's dx? Minus sine t dt. The only thing that's not there that I need there is the minus sign. So I'll get an extra minus sign floating around. And this 2, what do I do with that 2? Put it out front. That sine and the dt is going to give me the minus dx. This extra cosine is an extra x. Hey, wait a minute. X e to the x dx. There's integration by parts staring me right in the face. There's integration by parts. Right upside the head. And I didn't switch the limits because you don't like it. But you could. You could plug in 0 and pi to x and get x equals and x equals for those limits. But you see how making the double angle formula throw in here made this a problem we now can do with a method we, quote, understand. A math person is a lazy person. My goal is to take a problem I don't know how to do and turn it into a problem I do know how to do. Then use the tricks I already know. As often as possible, I want to do things I already understand. So I took an ugly problem in E and cosine and sine and said, nope, it's integration by parts. Better? Ish. You asked me this one earlier, right? Better? We're getting there. More questions. Believe it or not, that one I can answer. Why? Why? Okay. Almost all of this course is building towards Alpha 3. I'm going to ask you a big science question. How does light work? How do X-rays work? How do radio waves work? How does gravity work? How do ionic bonds work? How do nuclei stay together? What makes that happen? All of those are governed by fields. Strong nuclear field, the weak nuclear field, gravitational field, and the electromagnetic field. All of those fields work because of calculus. Maxwell, James Clerk Maxwell, discovered all of the electromagnetic fields in the world obey 4 rules based on integrals and derivatives. But those integrals and derivatives are 3-dimensional. They don't work just on a piece of paper. They work in 3-dimensional space because that's where we live. And so Maxwell said, I want to understand how these integrals and derivatives work. And lo and behold, all sorts of piles of trig functions, exponential functions, products, sums, divisions, stuff we haven't got to yet, all show up in these works. He says, this is hard. And at the same time he's saying this is hard, 20 other mathematicians, Euler, Gauss, Jordan, Newton, Leibniz, Cauchy, they're all writing papers about trying to make the math that all these physics people are doing work. And they develop all of these tricks. Say, oh, you came up with this because you think that's how an electric charge creates an electric field. Well, if that's the case, we need to be able to integrate things that look like this. Maxwell's 4 equations describe in a very real sense everything that operates in electric fields ever works. So, how does a radio work? How does an X-ray machine work? How does a CT scan work? Why don't nuclei fly apart just because there were protons stuck together? All fall through these sorts of integrals. So when the question is, why, God, why? Because thermodynamics told me the universe has to work this way. Physics said the universe has to work this way. And if it weren't for all you science people trying to understand things, I wouldn't do any of this shit. On my door in my office is a t-shirt from the Hayden Planetarium in New York that I bought in 1982. It says, in the beginning, the Lord said, and there are Maxwell's equations, and there was light. So why, God, why? Because he said so, and he said, let there be light. This is how it works. So believe it or not, I promise you I'm actually answering a theological question. I hope you all have a wonderful rest of your day. If you have further questions, I will be in the Enrichment Center from 2 to 3:30. If you have other questions, feel free to send me an email. I promise I'll try and respond. As long as I get it before 9:30 tonight, you'll get a response. Have a good one. I will see you all tomorrow.